Hello again. This is the Pencrest High School AP Physics C video series. This is video 1D, motion with unconstant acceleration. Now you will recall from last year the kinematic formulas. The same three formulas are on the AP Physics C formula sheet this year, but you need to know specifically when you are allowed to use them. These three formulas only apply when the acceleration is constant. Most of the time it will be, but you need to know when it's not so that you can know when you can't use them. Now, very often this year, position or velocity or acceleration functions will be presented to you in a format without units in the expression. In order to determine if the standard kinematics formulas apply, or these, all you need to do is look at the degree of the polynomial. The degree of the polynomial is the largest exponent on the independent variable, which in our case, in these cases, is usually time. For position, if the degree is 2 or less, you can use the standard kinematic formulas. The degree, of course, is the on the 1/2 AT squared term. For the velocity formula, if the degree is less than 1 or 1 or less, then you can use the V0 plus AT. If the degree of the polynomial is greater than what's listed above, then you can't use the kinematic formulas. Okay, so again, you need to know when you can use these and when you can't. The generic position, velocity, and acceleration formulas look like the following when there is a jerk term. Okay, again, this is a blue box. These are not on the formula sheet, but the extra term in each case I think is pretty easy to remember. For position, x equals x0 plus v0 t plus 1/2 a0 t squared. Those are familiar. Plus 1/6 jt cubed. J, of course, is the jerk term. For the velocity, v equals v0 plus a0 t plus 1/2 jt squared, and a equals a0 plus jt. Again, these are not on the formula sheet, so you'll probably want to at least remember what the extra terms are. Now, there is another simplifying assumption that's being made here, and that is that the jerk is constant. So the progression that goes from position, velocity, acceleration to jerk actually keeps going. There are more and more terms. The fourth, fifth, and sixth derivatives are called snap, crackle, and pop. They don't get much use, and there are additional terms. Physicists can't seem to agree on what to call them. They've been called lock, drop, shot, and put. There's no real reason for those, but it's just kind of fun to say snap, crackle, pop, lock, drop, shot, put. You won't see anything higher than snap on the AP exam, and they won't use that term for it because it's not universally accepted. You might see a third or fourth degree polynomial for position, and you may need to use it to quantify position or velocity or acceleration. But they won't use those terms to refer to the higher order derivatives. Now, if we look at a generic velocity function, let's say we're given the following: v equals 0.9 t squared minus 25 t plus 54. Again, it's just a polynomial expression in t that doesn't have any units in it. So what we need to do is sort of, based on just what the function tells us, we can get a lot of information from it. First, we want to force it to look like the generic version. The 54 is, you could consider it a constant. That's the initial velocity v0. We'll move that to the front here. Minus 25t, the second term is the AT term. There it is. There's the linear t term, and then 0.9 t squared. Again, there's a constant term, a linear term, and a quadratic term. Each of these is associated with our particular kinematics quantity. When you think about the exponent on the t term that's associated with each one and how this would be used ultimately to create units of velocity, we know that this term here is an acceleration term, so it's going to have units of meters per second squared. We're multiplying by t, so one of the seconds in the denominator goes away, and we're left with meters per second, which of course is what we want. The same thing happens with the jerk term here. So again, the constant term is the initial velocity v0. We know that at t equals 0, at the initial conditions there, the velocity is 54 meters per second, assuming meters in seconds. The initial acceleration, again, it's v0 plus a0 t. So the a0, the initial acceleration, is associated with this t term. In this case, the initial acceleration is negative 25 meters per second squared. The negative, of course, is included. The jerk term is associated with the quadratic, the t squared term. You want to be careful, though, because the 0.9, the coefficient, is 1/2 the jerk, because we know that the coefficient here in the velocity expression is 1/2 j t squared. So 1/2 j equals 0.9. Therefore, the jerk in this case is 1.8 meters per second cubed. Now, this velocity function has different signs in it. We've got positive, negative, positive. It typically means the object is going to change direction. We can determine when and where these changes occur by setting the velocity function to 0. Quantitatively, this will tell us when the object changes direction. So we take that velocity function and we set it equal to 0. We put it in standard form. You might recognize ax squared plus bx plus c equals 0. So we're going to use the quadratic formula to solve for the zeros. What we find is that, again, there are two solutions. They're both physically meaningful. We get t equals 2.36 and t equals 25.4. They're both physically meaningful results. The object is going to change direction twice after t equals 0. Now, in order to determine where it is when it turns around, we need to integrate the velocity function. Again, we took a derivative. We'll take a derivative later. We're going to integrate this velocity function to get the position. Again, the integral of v dt gives us the position. We're going to take this function, add the dt here, and then integrate. And we're going to get this expression here. The one thing we don't know, at least with this given information, is the integration constant. We don't know the initial position. Typically, we would be given that piece of information. If we had it, we would simply put the two zeros for t into the position expression, and that would tell us where it is at those particular times. Now, if we take a derivative of this velocity function, it's going to tell us the function for the acceleration. So dv dt. All right, we know how to take a derivative. The constant goes away. We go to the exponent to the 1 less, and then we take the 2 out front, exponent to the 1 less, and we get this expression here for a, negative 25 plus 1.8 t. Now, qualitatively, we can see that the acceleration is initially negative or to the left. As time goes on, its magnitude will decrease because the jerk term is positive. At some point, the acceleration will reach 0, and then it will change direction and point to the right, while then increasing in magnitude. We can determine when this is easily enough by setting the acceleration function to 0 and solving for t. So we see that negative 25 plus 1.8 t equals 0. We solve for t. we find that the acceleration equals 0 at 13.9 seconds. Now, this is the point in time when the acceleration is 0. It also represents what is called a local extreme of the velocity function. We'll see this when we look at graphical analysis, quantitative graphical analysis. This local extreme is either a maximum or a minimum depending on what the signs are in that velocity function. Our initial velocity is positive and decreasing because we have a negative acceleration term. We will see that this extreme as a local minimum will represent the maximum negative velocity before it starts going positive again. Okay, so we will see a number of functions, particularly in week 2 WebAssign, where you will have to do various manipulations, integrations, derivatives, and so on, and figure out where it is and what it's doing and how fast and when it turns around and all that good stuff. Next up, we'll look at some quantitative graphical analysis using the same quantities and the same principles. Until then, enjoy. I'll see you again soon.